everyone. So today we will discuss the way how to process JPEG encoding, decoding fully. So right here, there is the simple diagram of those necessary processing of the JPEG encoder and decoder. Okay, so how does it work? So in the beginning, so we do have a color image, so it doesn't really matter what image it is. So, and that image must be processed by few steps. The first, what is going on with the JPEG image is the pre-processing. So in the pre-processing, so the three color component image, which is the RGB, will be converted into the YCBCR. Such kind of conversion will uh, let us to spread, to disconnect the color component into the some other color space where the information about details will be separated from the information about the colors. See here inside of the RGB, the all colors are important. So we cannot technically kind of reject one of that color. So the degradation in terms of the image will be pretty much higher. So in order to keep like acceptable level of degradation, so what we need to do is to identify where is the objects, so where is the gradient, where is the detailed information about the image, and where is the information about the colors. We do have such kind of transformation which is called YCBCR. So, and the three-layer RGB image will be converted into the YCBCR. See here those boxes, they do have a same size. So and that size will be the same as the image size. Okay, so what is happening next? So we will have to process something that's called the color reduction. In the color reduction, Y component, which is actually information about the image details, will not be changed and will be directly transformed into the next consideration, so without any change. So the Y star is equal to Y. So in case of the CB and CR component, the CBCR, this is the color component or chrominance, and that information must be reduced. So technically what is happening here, so we will reduce each 4 pixel. Assume that CB component will be presented as this matrix. So what I did, I just simply load the Lena test image, convert it into the YCBCR and display the like 10 by 10 matrix taken from the CB component. Okay, so now let's discuss how to process the color reduction. So in terms of the CB, so what is happening here? So we will try to separate our image into the 4 pixel spot, like this, this, and so on. So Y4, that's the definition of this number 4. So technically, like the first number here is the Y component, and I am going to play with the 4 pixels from Y component. CBCR will be reduced into the 1 pixel. Okay, so how to do that particular reduction? So very simple. So here I will not keep those colors. I will keep only the first pixel. So no mean, no any filtering, just keep the numbers like this, like this, and so on. So here, instead of using the 4 pixel, so I will keep only first pixel in each 2 by 2 separate block. So and that will be our CB component, and so on. So after reduction, so that will be our final CB matrix. So again, in each 2 by 2 separate blocks of pixels, we will keep only the first, like in that block of the first 4 pixels, so we will keep only this number. And in each 2 by 2 matrices, we will keep only that particular number. Okay, so and that will be our matrix after reduction. So here we will just delete all of those non-necessary numbers. Okay, so that's why we can get like CB star. So the size of that CB star will be dimension wise will be like 2 times less compared to the original one. The same thing we will did with the CR. So the final matrix will be much smaller compared to the original size. Okay, so what is going on next with our JPEG encoding? So the next what we will need to do is to separate our image pixels. Right now that will be the pixels from component wise BNCR into 8 by 8 again separate blocks. So next, each 8 by 8 block will be processed by using the discrete cosine transformation DCT, which again can be very easily to be implemented. So after DCT transformation, so our block will be processed by the quantization. So the matrix Q is available, so we can always get it. So this is the standard matrix. So and in the quantization step, all elements in our DCT block will be divided by the corresponding elements from the matrix Q one by one. So and in the final stage of the quantization, so we will round that particular numbers, okay, and around it JPEG coefficient, DCT coefficients will be used in order to process the Hoffman coding. So the output of the Hoffman coding is our JPEG file. So the Hoffman coding, this is nothing else as the entropy coding. So where the information about the JPEG coefficients will be efficiently stored in the binary format. So as default, our JPEG image is nothing else as the set of JPEG of DCT coefficient, quantized DCT coefficient, compressed using the Hoffman coding. So this is the brief overview of the JPEG. So step by step in like all necessary details for complete understanding what is the JPEG encoder. So that original image mostly taken by the camera, and our digital camera is processing that steps always when we are saving our photos in the JPEG domain. Okay, now this is just the encoder, so that will happen in our digital camera. So the next what we will need to do, I want to display the image what I just built in any devices. So I can use the same digital camera to see my image, or we can use any other devices, including the computers and all others, to display that particular information. Okay, so what is the JPEG decoder? So every time when I want to watch that particular JPEG image, so I will process all of the steps what we handle in the encoder in the backwise order and in inverse manner. So our JPEG image, this is the compressed by Hoffman coding, the set of rounded JPEG DCT coefficients. So the first what we will need to process here is the inverse Hoffman coding. So after processing the inverse Hoffman coding, we will have exactly the same set of coefficients what we had here after the quantization. So here we got that exact information. Remember the Hoffman coding, this is the lossless entropy coding procedure, so where all information will be recovered exactly. So after processing that particular inverse Hoffman coding, so we will have the set of coefficients. So that particular coefficients need to be dequantized using the inverse quantization approach. So the definition is very simple. So in the beginning, we divide our DCT coefficients by Q. So here the coefficients what we got from the inverse Hoffman coding, I will multiply by Q. So by same standardized JPEG quantization matrix. So the next we will process the inverse discrete cosine transformation. So in order to get the pixels domain 8 by 8 matrix. So that particular pixels matrix will be moved back into the YCB or CR, depends where those initial 8 by 8 block came from. Okay, so after like rebuilding those Y star, CB star, CR star by completing that part of the Hoffman decoding of the JPEG decoding, so we will have to process the inverse color reduction. So in case of Y, no change, so that will directly move as it is, but in case of the CBCR, we will need to process inverse procedure. See right here, this is the CB what we got after processing the color reduction. So in order to implement the reverse YCBCR into the RGB, so I will need to fulfill the left numbers what does not exist right now. So the idea is very simple. So I will just place the same number here. So and finally we will get a matrix like this. So here, so these 4 pixels will be just copied, will be recreated using the first original pixel from the first 2 by 2 matrix. Like the second matrix, again, so we had only 104 coefficients, so I will just duplicate those coefficients and fulfill the empty pixels location. So same here, 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 and everywhere. So those for 2 by 2 matrices I rebuild. And such kind of procedure must be processed for the rest of our pixels. That again, so we will need to process. So this is something that's called the inverse color reduction. After processing that step, so finally we will get modified YCBCR. So they are not original anymore because they experience the compression done by the JPEG. So, and in the last step, what we are doing, the YCBCR will be transferred back into the RGB format. So, and the RGB format can be displayed in our screen. So that can be either a mobile phone, a tablet, PC, laptop, anything else, any other devices. So we can use in order to display that particular JPEG image. Okay, so this is the general framework of the JPEG encoder and decoder, and today I will show you how to implement encoding decoding for the JPEG using Matlab, like in the example. What the image what we are going to process here will be just the simple Lena image, color image. Okay, so and now let's try step by step, one by one, implement encoder and decoder. So for that we will need Matlab. Okay, so now let's make an empty project, an empty M file, and here we will make our first source code. Let's call it like JPEG encoder decoder. Okay, and the first what we need to do is to open our image. I will start from creating the function. I will just call it like JPEG encoder. Okay, so all CLC. So that will be our first few operations. So the next what we need to do is to read image. So in our task 1 JPEG folder, where is this image, Lena 512 color. So that image is possible to find in internet. So just Google like Lena color image. Download. Okay, so here, where is Lena color image? Okay, the better way to do that here, where is the standard test images from the Rice University, so, and better to get this image. So Lena 512 color TIFF image. So here where is even like okay, so grayscale. Yeah, so this one is better to have. So this is that image, TIFF image. Okay, and that image I am going to open. Technically, I can just directly call this image because this image is located exactly in the path what I need. So in order to read image, we will use the command imread. And 512 our diff. So let's call it as the matrix I, and what I will do is to convert the pixels what I have here into the double. So this is our image I. So as we can see here, it is like three-dimensional matrix. So as long as any color image they as default contains a three color component RGB, this is our RGB color planes of Lena image. So okay, so we found it. So the next what I will need to do according to my scheme, I supposed to process the RGB to YCBRCA converter. So for that, I will use the function. So in that function, we will create by ourselves. So I need Y, CB, CR. So and that will be our color reduction function. So input parameter here will be our image I, okay, and here let's place those color reduction scheme. Actually, here 411, this is the one possible way. So there are a few other different ways like how to handle the color reduction. So instead of 411, here can be 421, 422, 444, and so on. Any different combinations of those color reductions are possible here just in order to process those kind of reduction in a more efficient way. So the most common one is the 411. So that actually explain us why the color component they are less important compared to the details. So details always have more relevant information for us than the colors. So that's why the colors in the JPEG framework they are reduced. Like, and as we can see here, 75% information about the colors rejected by using the scheme 411. So this is the point. Okay, so and here we will use this particular 411 scheme to make our color reduction function. Now, how to make the function? I will just copy this part. Okay, so here let's create a new one. I can place it here and let's call it function. And save. Okay, so and as default, so the Matlab is asking us to create the function, color reduction function. Okay, so here state reduction scheme. So I will just display that particular number. I reduction scheme. Okay, so in that function, so the first what we need to do is to get our component R, G, and B. So the component R, this is our first plane of I. So in order to get it, so I is supposed to read all X, all Y, and the first Z. So in order to get a G, I will do the same, but here the second color plane. B is third. Okay, now the next what I need to do is to convert RGB to YCBCR. How to get Y? So I will process the floor operation in the end. So the conversion is just the linear combination of different pixels. 7 G plus B. Okay, CB. So this is 128 minus 0.168736 multiple R minus 331264 G and plus 0.5B. Okay, MCR will be 108 plus 0.5 R minus 0.18688 G. So this is our equation. Okay. So this is our YCBCR. Okay, and now, so if I reduction scheme 1. Okay, our modified Y. This is the same as original CB modified. This is our CB. So in here I will need to take only the first coefficient in each group of 2 by 2 pixels. So that's why we will easily express that case. And C RM CR 1, 2, and that's all. Okay, and that ym should be our output parameter, same as everything else. Okay, done. Don't forget to save. Okay, and right now we can check whether it works or not. So, and now we can see what is this. So our CB 256 to 56. Okay, original I 512 5123. CB CR has the size 256 to 56. Y 512 512. So that's exactly as it is displayed in our framework. Y exactly the same. CB is 25% from the original size. CR same 25%. Okay, this step is finished. Okay, so next, now we will need to process those other steps related to the JPEG encoder. So the first what we will need to do is to divide our blocks into the separate 8 by 8 blocks. For that, I will launch a loop. Okay, so as long as we are going to hold 8 by 8 blocks, so that's why in order to hold each block one by one, so here I will first need to identify the first pixel of this block. For example, for the block 1, the first pixels of that block will be 1, 1. That's exactly what I want. Okay, so in the first, what I will need to get, like divide image into the 8 by 8 block. Okay, so our block will be equal I E plus 7 G plus 7. Okay, and according to the JPEG procedure, I'm supposed to subtract 128. Okay, and let's see what will be my first block. Okay, so this is our first pixels block taken from the Lena image. So the next what I will need to do, process discrete cosine transformation. So let's call it like block DCT, DCT 2. Block DCT, block, let's see. Okay, so this is our first DCT block. So we can see a lot of coefficients. The first is the DC coefficients, which has a meaning similar to mean value. The other one presents the different frequencies according to the discrete cosine transformation over the two dimensions. So this is the set of pixels, what set of coefficients, frequency coefficients, what we get after the discrete cosine transformation. So the next what we need to do is quantization. Okay, done. So what is our quantization? We need the metric skew. As long as the metric skew, this is the standard metrics, so we can easily get it from internet. So I will just copy paste it from my previous course. So this matrix again is the standard. So the most serious and interesting part of the JPEG compression. So each coefficient here has a proper meaning. Actually, those coefficients, they define the power of the JPEG. Okay, so now how to process quantization. Again, like block DCT, let's call it Q, quantized. So I supposed to round my coefficients. So in here the block DCT will be divided by matrix Q. Matrix Q is given here. Okay, so quantization done. And the next, what I will need to do according to my scheme is the Hoffman coding. So the Hoffman coding is pretty complex, so that's why let's say we process it offline. Okay, so right here I supposed to get a binary stream. So in that binary stream is nothing else as our JPEG path. Okay, so and at the same time, what we can do, we can process the decoder. So the idea here is to process the whole JPEG encoder decoder step in one framework in order to display what will be our image after compression. So if we can get the image with the acceptable quality, so means that we process all of our steps without any issues. So in reality, for sure, like in this step, I supposed to process the Hoffman coding, get the all coefficients in the binary shape, save the JPEG file, and process it later. So right now we will avoid, like we will skip that step, and we will go to the JPEG decoder. Where is the one problem here? See, in order to process the JPEG decoder, so I supposed to know, I supposed to process CB and CR after processing Y. So means that I cannot even start doing those process without taking in consideration the component, the chrominance component, color component, CB and CR. So in order to do that, so here I will save my block like quantized block of I, like this is originally I, into the some matrix y star, and I will place that 8 by 8 quantized set of coefficients into the exactly the same set of pixels. And just for instance, let's say, how does it work? So in here display block DCT. Oh. So this is our block DCT, and this is the block of the quantized coefficients. And actually we can I also see that those coefficients, they are located in the matrix y star. So that y star matrix I can identify, like design in the beginning. So that will be size I. Okay, and here, stop. Yeah, 512 double. So build from zeros. And here we will process it. Okay, so after processing all of this loop, so I will have complete y star. And right here we can see a lot of coefficients. Here, this is our blocks. So we can even see them. All of those non-zero coefficients, they are our DCT coefficients. Okay, so the next step is to do the same for the CR and CB and CR component. So as long as those procedure is exactly the same, see here for the Y, CB, CR, they are processed through the same framework, except we must use the different quantization metrics. Okay, so here I cannot use I anymore. That will be the CB. Okay, so in here, process CB CR. Okay, so here I supposed to use CB. Okay, so I cannot use the original matrix because this matrix Q is designed for the luminance component for the colors, but for chrominance, like for color components, I need another matrix. So in that matrix, I will again copy here. So this is the matrix. So as you can see here, most of the numbers are 99. So it means that most of the chrominance coefficients, they are not really important compared to the details information from Y. So that was the reason why we process such a massive reduction for the colors. And at the final stage, we will see this that not damage our image much. Okay, so here I will use QChro. Okay, so I can build my CB CR star matrix. CB CR. Okay, block from CB, process block, divide by chrominance. Okay, and here I can use like CB star for our block. Okay, as long as I do have the two components, so I can divide. So here the first CB. So and in the same loop I can process CR as long as the size of those two components same, so we can do that. So the rest I don't really need to change. So here will be the CR. So that's all. See, when I process the CB, so we are taking the pixels from the CB matrix, subtract 128, process DCT, and quantized using the chrominance Q matrix. After quantization, that particular block I will place into the matrix CB star. Okay, done. So at the same time, for the same I and J, I will process the CR matrix. So see, now the block is taken from the CR matrix. So this step, like those two steps, DCT and quantization will be exactly the same as before, except that block is taken from another image. Okay, and finally I will save that particular block into the CR star. Yeah, that's all. Okay, this part is done. So now let's see how does it looks like. Okay, so here the important part is our Y star, CR star, and CB star. So 256 to 56, to 56 to 56, 512, 512. So and those matrices, they are built by using the coefficients, like that, quantized coefficients before processing the Hoffman code. So technically we stop here and keep all of our quantized DCT coefficients into the matrices with the size similar to the Y star, CB star, and CR star. So they are not exactly those particular colors, but now they contains our coefficients, like you can display like C star. So and we can see there are, as long as like those color components, they are less important, so those coefficients here will be like less significant. So the next, what we will need to do is to process back all of the steps related to the decoding. So here one by one, let's process those operations back. So for that, I will come back to our first procedure, and here we can start decoding our pixels values. Now, for example, what we will need to do here is to process the inverse quantization. Inverse quantization. So for the inverse quantization, so what I need to do is to process our quantized coefficients, but here instead of divide, I supposed to multiply by Q. So that will be our first step. Once again, here, the coefficients, what is coming from my Hoffman coding, I will need to multiply by Q. By the quantization matrix. Okay, so this step is done. So the next, what I will need to do is the inverse DCT. So for the inverse DCT, so here will be our block DCT star. So that will be the inverse DCT2 taken from the block DCT star. So that will be our inverse DCT. So in the next, what I will need to do is to move our pixels back. So actually what I can do is place it here. This is our Y star. Instead of that block, I will do this round block DCT star, and as long as in the beginning we subtract 128, so here I'm supposed to add 128. So and this is that one will be our Y star path. Okay, and the similar decoding procedure, so we will have to process for CB and CR. Here. JPEG decoding, so star. So from here, but instead of Q, I'm supposed to use the chrominance Q. Okay, so this step finished. So inverse DCT star, that will be exactly the same. So, and now, instead of Y star, so here is supposed to be CB star, round, block DCT star plus 128. Okay, done. Processed well. So, and I also supposed to process the JPEG decoding for the CR component. So here it's correct, correct, correct. So what I need to do, instead of CB, add CR and delete this part. Okay, so this is our C star, CB star, CR star, CB star, and Y star. So what we process back here, and we got that particular number. So now what we need to do is to process the inverse color reduction, get Y, CB, CR. Okay, so what we can do. So the first of all, here we can see that I need to build compressed color image from Y star, CB star, and CR star. So to do that, the first what I need to process, see in case of Y, that will be directly moved without any issues. But in case of the CB and CR, we will process some coding. Okay, so okay, let's call them modified. Y modified. So that will be our I star. So now CR modified. So that should be the same. Should have the same size as Y. So our Y is the size 512 over 512. So that's why I can use it here. So this is our CR mode and CB mode. That will be the same. Okay, so definitely I cannot keep those zeros, so I will need to rebuild my CB modified matrix. See, my CB matrix should be have same size as Y, 512 over 512, but original size is 256 over 256. So actually, each pixels from that CB matrix I need to duplicate 4 times and finally complete our this matrices. Same what we processed here. Okay, so now what I can do is, let's do this. 1, 2, and 1, 2, and equal CB star. Once again, so what is happening here? So this first pixel, so I will place everywhere into my matrix with the coordinates 1 with the step 2 until n. So that's why I will take this coefficient, this coefficient, this coefficient, and all others, that coefficient, and all others in the y direction. And finally, that will be my CB star. Let's see, how does it looks like? Okay, see here, I place the first coefficients everywhere into the first position of the 2 by 2 matrix. Okay, so the next what I want to do is I want to place somewhere here, but that should be again, that pixels should be the same as these pixels. So these pixels should be the same as that pixels, and so on. Okay, so that's why I will copy it here. So here, instead of like 1, okay, this is like X, Y. Yeah, let's change here. Okay, so now I place that number here. Okay, so the next, let's try here. So let's make this part. So now we can see the numbers appear everywhere here. Okay, and the last one should be 2, numbers 2. CB1. Okay, so now we can see that all numbers are fulfilled. So, and the same I will need to do with the CR. So it will be exactly the same as long as our matrices have the same size. Okay, and let's check whether it works or not. Like CB mode, CR mode. Oh, it's all the same. Yeah, we can see this matrix is pretty much same. Again, that's explain why We don't really need the CR matrices in such an expensive way as we use for matrix Y. Okay, technically done. So now we are here. We got Y, CB, CR. We call it Y mode, CB mode, CR mode. And now I will need to process the inverse conversion into the RGB component. So the first what we will need to do here is to convert our Y mode, CB mode, CR mode back into the RGB component. Okay, so here convert Y, CB, CR to RGB. Okay, similar to what we did before. Let's say I will create like modified red, green, and blue. So in here I will use the color reduction inverse function. Okay, and input parameter will be our Y mode, CB mode, and CR mode. So and that will be the function which must return our original like red, green, and blue. As long as we process the compressions, so those RGB will not be the original anymore, they will be the modified somehow. Okay, for that I already built the function color reduction inverse function. It is here. So inside of that function, so YCBCR, this is the input parameter. So in the beginning, I will create RGB, which is the matrices, same size as Y, as long as we must keep same size for the YCBCR, same as the original image size. So I will just keep it here. And this is the equation how to process YCBCR back into the RGB. Okay, so just like process that particular calculation. So and inside of our JPEG encoder decoder, so now what I will need to do is to finally build an image. So here I say build and modify image. Compress. JPEG compress. So that particular image will not be the like the set of the binary coefficients, like the string of bits. So what we got here when we process our JPEG, so here that will be the BMP, like big bitmap image, which we create using that quite long way of different conversions regarding the JPEG compression. So finally we can get the original, like the real JPEG image. So we will see the pixels in our screen. So and for that, let's create like modified image IM. So and in the first plane of that image, I will place my red component. So and in the second plane, I will place my green component. Third plane will be our blue component. Okay, and the last what I need to show is to display my modified compressed image. For that we will use unsigned integer 8 command, because our initial function cannot hold double numbers. So n title, let's make some title. JPEG compressed image. That's all. Okay, so this is our JPEG compressed image. Now let's see the difference in between original image and JPEG compressed image. For that, I will display original eye. So this is the bitmap image, so original image before compression. So here I will use figure to show. So I will edit, run. Okay, so this is our compressed image, this is the original bitmap image. So for sure, if you will directly compare the different zone of that image, you will see the artifacts. Why? Because this is the JPEG compressed image, so a lot of information about the colors go removed from the JPEG image compared to the original BMP image. But anyway, this is the way how does it work. So in this particular example, we started from the original BMP image and we got the JPEG compressed image. So we avoid the Hoffman entropy coding. So, but anyway, we can see that particular image. So that's all what I wanted to tell you today. Good luck.